Okay, so have you heard about this guy Blaise Pascal, French mathematician, long curly hair, or really it was probably a wig since he lived in the 1600s. Anyway, he came up with this thing called Pascal's triangle, where you start with a 1, and then on the next row of the triangle, you put 2 1s. And then from there down, you start each row with a 1 and end that row with a 1. And anything on the interior of the triangle comes from taking the 2 entries above it on the left or the right and adding them. So 1 plus 1 equals 2. Here's a 1. 1 plus 2 equals 3. 2 plus 1 equals 3. And here's a 1. Here's a 1. 1 plus 3 equals 4. 3 plus 3 equals 6. And so on. You'll notice it's nice and symmetric. The right side always echoes back what the left side was doing. And so on and so forth forever. So that's just what Pascal's triangle is real quick. And there are many things that you can relate back to Pascal's triangle, many things that are cool about it. One thing to know about Pascal's triangle is we refer to this first row as row 0, not row 1. So then this is row 1. This is row 2. And by row, I mean all the way across here. It's row 2, row 3, and so on. You could say that one way of thinking about it is the number of the row matches the second entry. Second entry in this row is a 1, second entry in this row is a 2, etc. So row 1, row 2, row 3, row 4, and so on. Now, one of the most common uses of this is we use this when we expand binomials. And what does it mean to expand a binomial? Well, first of all, remember a binomial is a polynomial with 2 terms. There's a binomial. So how would I expand that? Well, I wouldn't. If I were, however, raising that to a power, expanding it basically just means multiplying it all out. So we can use Pascal's triangle to help us with that, and here's how. Look at a couple of basic expansions. This is x plus y, that binomial, to the second power. That means I'm multiplying x plus y times x plus y. I would use like FOIL or distributive property to do this, and I would get this as my answer. X plus y to the third. That's x plus y plus x plus y plus, x plus y times x plus y times x plus y. And again, you'd have to go through the process, like maybe multiply these 2 first. You get this, and then take that and multiply it times this one. And this will be your final answer. And you could certainly keep doing this and doing it the long way, and it would be kind of messy and tedious. Or we can use Pascal's triangle to help us, because it turns out that each row in Pascal's triangle gives us coefficients we can use to do this. Notice that this is a 1, this is a 2, and this is a 1. If you look at row 2, 1, 2, 1. And this is a 2. So row 2, and I take an exponent of 2, and it will have these coefficients, these numbers, they will be coefficients in that binomial. Exponent of 3, look at row 3. You have 1, 3, 3, 1. 1, 3, 3, 1. And it keeps going like that. So for instance, for x plus y to the fourth, I would expect the coefficients to come from this row, 1, 4, 6, 4, 1. So that means I'm going to have something that looks like 1, 4, 6, 4, 1. But then what else am I going to have? Well, just like up here, you do have variables. So here's what the pattern works with variables. You got basically a pattern for the coefficients. That comes directly from Pascal's triangle. You have a pattern for the first term. This is the first term in my binomial is x. Okay? X to the fourth is going to be my highest degree that I have in this particular binomial expansion. So I'm going to start with that, x to the fourth. Then I'm going to count down, x to the third, x to the second, x to the first, and then I've got x to the 0, but I really don't have to write that. But this would be x to the 0. So 4, 3, 2, 1, 0. Then I go to the second term. There's a pattern for the second term. Basically 3 patterns. One was the coefficients, then the first term, then the second term. Second term starts off with 0. Remember, we ended up with x to the 0 here. This starts off y to the 0. Don't have to write it because y to the 0 is 1. Y to the first, y to the second, y to the third, and y to the fourth. This is my answer. Usually I probably wouldn't write these ones, but that's the answer. That's what you get if you multiply out x plus y 4 times. Another pattern to notice here that's really helpful because it can help you if you get stuck in the middle of it, if you're not sure where you are. Notice that the degree of each of these terms is 4, meaning that the number of variables in each term adds up to 4. So this is 4, 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, and that's 4. All right, so let's look at x plus y to the 5th. Excuse me. Or let's change our variables. Let's use a plus b. A plus b to the 5th. Pull out our Pascal's triangle. We should expect the coefficients to be 1, 5, 10, 10, 5, 1. Interestingly enough, another actually interesting pattern, both with the binomials themselves and with Pascal's triangle, if it's a power of 2, you're going to have 3 terms. Power of 3, you have 4 terms. 1, 2, 3, 4. Power of 4, you have 5 terms. Just like on the 4th row, you have 5 terms. 5th row, 6 terms. 7th row, 6th row, you'll have 7 terms, and so on. So this is going to have coefficients 1, 5, 10, 10, 5, and 1.